This is the first of two programs. Hybridization, first of all, for single bonds. Hybridization is the blending of atomic orbitals to form new orbitals that explain the observed geometries that we see. For instance, let's consider methane. Here's how the electrons are arranged in the atomic orbitals of carbon. We can also represent it by this orbital diagram, where we place the electrons as follows. The first thing that happens in the act of hybridization is to promote an electron. We take our 2s and we take that electron and promote it up to the 2p orbit. So we now have one electron in each of our orbits. We then blend these orbitals together, an s and 3 p's, and they form what calls an sp3 hybrid orbitals, 4 of them, all equal with one electron in each one. So this would be what that arrangement looks like, because as we know, electrons repel each other and they will then form a shape such that they can minimize their repulsion, and that would be a tetrahedral. There is now one electron in each of those orbitals. In the next diagram, we bring along hydrogen to now unite at the ends of each of these bonds. So the hydrogen's electron is represented by the green arrow, and the circle that represents the orbital diagram of hydrogen, and it now bonds at these locations. Notice that the orbitals match the geometry that we need, a tetrahedral arrangement as shown in the ball and stick model. Let's go back to the atomic picture we ended up with for a minute. This shows the atomic orbitals that are involved. I have the atomic orbitals of hydrogen represented by the spheres, and the sp3 hybrid represented by the carbon. Those orbitals essentially will form the following picture. Recall that orbitals show the most likely place to find in electrons. So the dots here represent the nuclei of our carbon and our hydrogen, and it's showing the most likely regions where we're going to find the pairs of electrons. Just a note about the overlap between the hybrid orbital and the atomic orbital of hydrogen, which we see at these 4 locations. These are called sigma bonds. Sigma bonds result from the overlap of s, p, and hybrid orbitals on their ends. Let's look at this in a case of a water molecule. Oxygen has the following arrangement, and we can picture it this way, with all of the p orbitals having electrons in them, and the s orbital is also full. We're going to blend together this s and the 3p. Again, that'll form an sp3 hybrid. It's going to be populated a little bit differently than our previous one because we have 6 electrons to accommodate. But because we're making sp3 hybrids, 4 of them, they're also going to form a tetrahedral to get as far away from each other as possible. And the electrons will populate the orbitals as shown here. 2 of the orbitals are full, so I'm going to ignore them in my next diagram because they're unable to hold any more. This would be the remaining orbital then with hydrogen bonded with it. Notice that the orbitals match our geometry of a bent molecule for water. Again, we can locate the sigma bond as the overlap between the s and the sp3 hybrids. Let's now move on and consider boron trihydride. Boron has the following arrangement. Now you need to recall that boron is one of our rule breakers. According to Vesper theory, it can only accommodate 6 electrons, or 3 pairs. That 3 pairs means that we only need to blend together 3 orbitals. So these would be the ones involved, leaving one of the p orbitals unaffected. They would then blend and make the following arrangement, an sp2 arrangement. This is trigonal planar in shape, with bond angles of 120 degrees. Along comes hydrogen that connects at the end of each of these orbitals in our sigma bonds, and we end up with this trigonal shape that we have for boron trihydride. Now let's consider beryllium dihydride. Here's beryllium's arrangement. Remember that beryllium is also a rule breaker and capable of only accommodating 4 electrons, or 2 pair, requiring 2 orbitals. So we only need to blend together these orbitals. This is called an sp hybrid, involving only one s and one p, and our electrons would arrange themselves as follows. 2 orbitals are now left unaffected. This shape is linear. So when we bring along our hydrogens, they'll overlap at the ends of our sp hybrid in the following. This, a linear molecule. Let's summarize what we've learned so far. Our electron regions demand certain types of hybrids. So let's look at our first two models, methane and water, both with 4 electron regions. They require an sp3 hybrid, and the sp3 hybrid has a tetrahedral shape with bond angles of about 109.5 degrees. So the Lewis diagram predicts the number of electron regions, and the number of electron regions dictates the hybrid. In my next case, boron trihydride has 3 electron regions. That then demands the formation of an sp2 hybrid, trigonal planar. And in our final example, beryllium dihydride, that has 2 electron regions. 2 electron regions will always require a linear sp hybrid. Remember, questions are always welcome, and thanks for watching.